Andy, I think you muted.
Okay.
Good. Okay. Oh, very good.
So now I would share screen.
Yeah, I can start sharing the screen.
Like this.
Still have 2 minutes, so no worries.
All right. So things seems to
Okay.
be.
Yeah. Okay. Let me give a quick introduction. I guess we can. Yeah, a bit early. Let's start. Yeah, it's a great honor and a pleasure to welcome Professor Andrew Yao. He's a Dean of the Institute of Interdisciplinary Information Science in Tsinghua University. He's also a distinguished professor at large in the Chinese University of Hong Kong. He was a full professor at Stanford University from 1976 to 1981, and Princeton University from 1986 to 2004. In 1996, he was awarded with the Keynote Prize. He received a Turing Award in 2000 in recognition of his fundamental contribution in theory of computation, including complexity-based theory and cryptography, communication complexity. Recently, in this year, 2021, he received another very prestigious award, Kyoto Prize in advanced technology. So today he's going to talk about probabilistic reasoning in machine learning. Yeah, please, Andy.
Well, thank you, Dr. Dong, for the very nice introduction. And first, let me thank the organizers for giving me this chance to share some thoughts with the audience. And let me first say a few words about the background of the subject. Many years ago, when I started working as a computer scientist, almost the first subject in computer science that I encountered is the mathematical analysis of algorithms, which was promoted by Professor Don Knuth. There are so many interesting results, and I was fascinated by it. For example, with Professor Tony Hoare's design and analysis of the quicksort algorithm. And I kept my research interests in the mathematical analysis of algorithms from that time on. And so initially I worked in searching and sorting type of algorithms, and over the years, in more recent years, in theory of auction and Bitcoins. And most recently, I got interested in the mathematical analysis of machine learning algorithms. And so today, I would like to share some of my recent results and thoughts on this subject. And the outline of the talk, I will begin with some introductory words about the field of machine learning, and which is a new algorithmic paradigm that has wide applicability, but little theoretical understanding. And because it's quite different from the traditional methodology of algorithm design. And so the research issues are a little bit different. And so I would come to that and explain why the mathematical analysis of algorithms, of machine learning algorithms, I believe is a very interesting and rich field worthy of further exploring. And then I will talk about the particular result I would like to mention. And first I will mention the field the example comes from, and then I will present the results, and then I will conclude. So machine learning algorithms are being widely used in all domains, as you can see, in medicine, in automatic driving, and so on and so forth. But the quality of solutions really rely mostly on empirical evidence. Compared to the traditional algorithms, there was little theoretical backing. And so it's fair to summarize the current state of affairs in machine learning as the machine learning algorithms run far afield of the scientific understanding of the subject. And because it's very different from the traditional algorithm design philosophy, so we have encountered bottleneck problems that are very distinct. And one, for example, the robustness problem is one of the big issues of the current state of affairs. And so how to improve the stability of machine learning is very important. And this is a very well-known example that if you use the classifier, the pattern recognition, to try to classify the picture, it would do it very nicely. However, you will, if you put into some noise, and in some cases, you will become something which will be recognized as an airliner, and therefore Pig Can Fly becomes a very apt description of the phenomena. And also, because AI and machine learning, they are widely used. So therefore, the criteria for the design of algorithms have some criteria that is different from the traditional one. And among all the applications such as governance, environment, medicine, and education, there is the question of the acceptance of the machine learning algorithms. More definitively, it's a big subject. The explainable AI is a very important hot topic. So the transparency of machine learning is a big problem for products that would require a high degree of public trust. So let me just illustrate with the following very simple example. And as we mentioned, that we have good machine learning algorithms that seem to work very well. However, we don't have the traditional proofs to support the assertion that that it works very well and other properties. So, for example, if you use machine learning that design a home appraisal AI system, so that means that the machine learning algorithm would take the data from the houses and their prices and the market in the neighborhood, then it will come out with a program that will be able supposedly to evaluate the new homes on the market. The prices is supposed to work very well. And suppose you have such a system, and if a customer comes to the sales office, and the system comes out with a estimate of the price to be $2 million, and the customer will be, it could get very upset or puzzled because he doesn't understand how the system works. So he would wonder whether the price could be trusted or not, because it could be designed that is biased toward this particular buyer. So to be able to design AI algorithms that can be explained to the experts and to the public, it becomes very essential, especially for products that are very widely used. And so this all comes from the fact that the machine learning algorithm model is a clear break from the traditional algorithm design philosophy that we employed until recently. And the traditional design of algorithms, the philosophy in computer science, is that you would study the problem very thoroughly, and you understand the mathematical structures very well until you reach a point that you can find efficient algorithms that can actually solve the problem and optimize the solution very well. But for machine learning algorithms, especially for the deep learning algorithms, it really comes as a black box. And so there's no real rigorous way to explain why the machine learning algorithm works. And thereby, people would wonder whether the designer have put in some bias into it. For example, in cases where, for example, the home appraisal, that the law specifies that you have to have some sort of anti-discriminatory type of properties. How can we check that? So therefore, to analyze the behavior of machine learning algorithms is a very urgent issue for machine learning and for the AI applications in general. And so that means that the mathematical analysis for algorithms that I mentioned that have a long history becomes especially interesting for current machine learning algorithms. And we would like to be able to certify that a machine learning algorithm, whether it's good or bad, we would like to be able to have an understanding up to the level as the traditional type of algorithms. As we mentioned, the robustness, whether the solution is stable with respect to noise or even more seriously to adversarial type of attacks. And the explainability problem is the solution backed by the sound reasoning. Is it consistent with the law that is relevant here? And now, because especially in machine learning, the probabilistic algorithms are the standard model. And so everything would involve probability in the analysis. And so the probabilistic reasoning often plays an important role in solving these challenging issues. And we would like to give an example in the context of the analysis of algorithms. And now the problem, the machine learning algorithms that we are interested in would come from something called the kernel method. And kernel methods is a type of algorithms that has been used widely in pattern analysis and in other domains. And before the advent, before the popularity of the deep neural networks, the kernel method actually were the most widely used algorithms in theory and in applications. And a kernel method would employ something called a kernel function. And in essence, it is a similarity function so that it can compare the input that you want to compute the function on. You can compare it with something that you already know, with some labeled samples. And so the kernel method is specified by a kernel function or a similarity functions to predict whether data points belong to some cluster or not. And the familiar examples include the linear kernel and the Gaussian kernel. And in practice, the Gaussian kernel probably is one of the most used kernels in practice, and it works pretty well. And now, as we mentioned, we not only want to understand why the algorithm works when it works well, but also when it doesn't work well, we would like to be able to analyze it. So one case that has been well known that for which the kernel algorithms don't work well is the parity function. And now, so experimentally, it's very well documented, and the plausible arguments have been suggested, but there's no rigorous proof. So we would like to prove that the parity function is hard to learn, at least for the Gaussian kernel. As it turned out, even for this very simple question, the analysis turns out to be much more complex than one would imagine. And let me explain about the definition of the kernel function. A kernel function K is a similarity function that maps a pair of points in n-dimensional Euclidean space to the real number. And it satisfies the condition of positive semi-definite condition. And by that, we mean the gram matrix associated with this similarity function, which is an n by n matrix. And its entry, the entry ij of this kernel is so the ij's entry is exactly the value of the kernel function with the first argument xi and the second xj. And so the requirement is that this matrix itself is positive semi-definite for any m points, x1 to xm. And so learning a Boolean function with the kernel as follows. So it comes in two steps. So given this kernel K that you can compute, you can learn a Boolean function as follows. So what we do is that we first collect data. We will take m random samples of points. So since it's a Boolean function, each sample point would come from the vertex of a Boolean cube. Instead of the 0, 1 n Boolean cube, let's encode it as 1 and a -1. So it's still n-dimensional cube, except that the width is 2 instead of 1. And so we will take m's random samples from a particular distribution you are interested in from the Boolean cube. So we will take m random samples, and we will learn through these samples to construct a function that will predict if I come up with a new point that we have not seen before. And so we will build an optimal model P for the Boolean function f. So what this means that we have a particular algorithm, that procedure that would find m plus 1 real numbers, a1 to am, and plus a single real number b, such that the following two conditions are satisfied. Firstly, it would fit the data, namely that if I take the linear combination of the following form, the summation of ai times k of xi, xj, and minus b, this linear function would have the same sign as the Boolean function we would like to compute, either 1 or -1. So it means that I would need to build a formula in such a way that if I use it to check with the data, you would have the correct sign, so that if I use the sign of this linear function or in a way that I would describe, that it will predict the correct answer for the sample points. And now there are many ways you can fit the data with the parameters A1, AM to B. And among all these possibilities, we would like to use the following optimization criteria. We would maximize the margin, namely that among all the parameters A1 to B that can satisfy the first fitting condition, I will pick one such that it would maximize the minimum of this expression, namely that if I look at the data point and look at what's the smallest distance from zero in all these calculations, the result would be optimal. We're going to see a intuitive interpretation of this in the next slides. And now, after I have picked fixed the parameters, and now I've got a predictor, which is a function P, that if I give you a new point that you have not seen before, a Boolean value, P will predict the value of Fy to be the sign of the value of Py, namely that I would put Y here and compute this linear function, and whether it's positive or negative will determine my prediction. And the error probability of P is then given by this. It's that how many fraction of the points I would make the wrong prediction. I'm here using 1/2 to the n because for simplicity, I'm assuming that the distribution is the uniform distribution. If you have a non-uniform distribution, then this error probability should be modified as appropriate. And now let's see the two probably most popular kernel method. The first example is the linear kernel. In this case, the kernel between two points or two vectors is simply the inner product of these two vectors in Rn. And in this case, the predictor, and if you look at it, the predictor Py is really a function in Y, because that all the other quantities have been fixed, because all the x1 to xm, they are properly substituted into it. So the net result would be just a linear function in the variables Y. And so therefore, if you look into the function in the domain of the in Rn, it's just a hyperplane. And so the hyperplane would, the fitting condition saying that the hyperplane should separate the two clusters of the sample points into the two groups, either true or false. And now the second condition, maximize the margin, it's meaning that among all the possible hyperplanes that can separate these two groups of points, it will have the maximal distance to the closest points among all the sample points. So this is because intuitively, this would ensure that you will get the maximum margin, and therefore it probably will correctly predict more function values than wrongly. And the second example is the Gaussian kernel, and in this case, the similarity function, the kernel function, between 2 points, y and y prime, is the exponential to the minus lambda times the distance square between the 2 points. So here, we're just taking it to be the Euclidean distance as the norm, and where the lambda is a parameter, because intuitively you probably want to pick a lambda so that it will have the appropriate influence on the result. If lambda is too small, if lambda is too big, or too small, it will not properly extract the desired information depending on the distance. So you would probably want to choose lambda into a range so that the exponent is a sensible number. And so the predictor now, according to our procedure, would be given by such a formula. And so when you have ny, you just compute its distances to all the points in the sample, and then weighted their influence appropriately, and you come up with this linear combination. And so Gaussian kernel is one of the most commonly used machine learning methods. It's producing satisfactory classifiers in many scenarios. And the popularity and the experience of the Gaussian kernel lies in the fact that it is a nonlinear function, because you can imagine that for the linear kernels, they are limited in their ability. Whenever you have a Boolean function that cannot be separated by a hyperplane, then your method would indeed produce errors. And however, in many cases, if you do a nonlinear transform of the input into something called the features vector space, the problem in the feature space would become linear separable. And the Gaussian kernel is something that you can see that it's not only it is not a linear function of y, but actually it contains all the polynomial terms. So therefore, that explains that why it works well in many cases. And now of course, the Gaussian kernels don't work well all the time, and but we don't really understand why it works so well and why it doesn't work so well. And the question is that what is its limitation and why? And there have been a lot of interest in this, and I think that it's still a subject of quite a bit of interest. And now we'll focus our attention on the phenomena that empirically that the Gaussian kernel method doesn't work well for learning the parity function, and we would like to confirm it analytically. And let me just review briefly the history of about the parity function. Previously, Minsky and Pepper many years ago proved that the perceptron cannot compute parity. And many years ago, Aspinis et al., they showed that no small degree multivariate polynomial can approximate parity well. So what this means is that if you don't use a Gaussian kernel, if you use a linear kernel, or indeed any bounded degree kernel, then this theorem says that you will not be able to approximate parity well. Now, but the Gaussian kernel actually avoid that theorem, so there's still a chance that it might work well. And the more recent discussion about the Gaussian kernel and parity function is by Benjo et al., who observed that very large lambda, the parity function, can be expressed exactly as a linear combination of n+1 Gaussians. And now this kind of doesn't contradict the idea that the learned Gaussian kernel predictor wouldn't work well, namely that the particular parity combination that they constructed is not of the form generated. It doesn't depend on the sample space. In other words, it is something that you don't need to learn. It's just something, it's just mathematically, it's there. So so actually, if you want to learn it, you will not come up with this linear combination. And but interestingly, the fact that it can be expressed as a linear combination of a small number of Gaussians means that the problem is not trivial. The problem is not with the power of representation, but it has something to do with the learning procedure. And Bengio et al. Also in the paper suggested some non-rigorous arguments for Gaussian kernels, and indeed for a class of kernels that why it wouldn't work well, the parity function. And what we would like to do is to show that the Gaussian kernel cannot learn parity for the various ranges of lambda. And so here in this talk, we will just prove it for a special case, just to illustrate the flavor and how the probabilistic the reasoning comes into it. And so the theorem statement would be something like this. And it says that with probability 1 minus little o of 1, namely 1 minus a term that goes to 0 as n goes to infinity, and you can show a random Gaussian parity predictor P will must have an error rate that is 1/2 plus little of 1. So what it means is that if you use the Gaussian kernel method, you will come up with a predictor which will wrong almost exactly 50% of the time. And the theorem's proof involves the probabilistic reasoning. And the key to proof is to set up a high-level view that reduces the problem to simpler pieces. And each piece by itself would require solving a non-trivial stochastic process problem. And the proof outline is the following. And let's consider m random sample points, and it will produce a parity predictor P sub x. So this predictor would depend on the sample point. And let's say it is A1 to AM and plus a constant B. It's useful to regard the predictor Px as a function that hashes a new value y into a into a function, into a real number. And let's first prove the result under the assumption that the AI is plus or minus 1, that's equal to the parity for all I. And we'll construct a probabilistic argument, and we'll come to that in the next page, to show that for a random sample set, x1 to xm, with high probability, the predictor will act as an effective hash function that would disperse points to random values. And so in some sense, and thus the Px cannot well separate points with the odd and even parity. So it would hash all the points. So if I just give the Px arbitrary point, some random points that's not in the sample set, whether they are parity plus or minus, they would disperse well into random values. And thus the Px cannot distinguish between the even or odd parity, and leading us to conclude that the error rate indeed will be almost exactly 1/2. And so let me explain the central probabilistic arguments that we mentioned there. And so the central probabilistic arguments will have a number of parts. And we're starting by proving the following lemma for suitably chosen small values of t epsilon. So t and epsilon would take on values to be functions of n, so that it would go to 0 as n goes to infinity. And we would define a subset of the pair of points. So essentially, I would define this set to be the pair of all points on the Boolean cube that have a fairly large distance between them. So they are not very close together. But on the other hand, all the pairs in the Boolean cube are almost all somewhat far away. So this A essentially it's very much almost exactly in measure equal to the same as the total possible pair of points. And let's define a predictor to be bad, that is as a hash function. If the probability that it would hash two random values together coming from A have a non-trivial, although if epsilon is small, but it's a properly chosen. It's not too small, so that if the hash function would fail to hash pair of points into some distance apart, then we consider it's failure. And so if the probability of separating points in the hash function, the failure rate is not trivial, then we'll call the predictor to be bad. And so the basic lemma is just to show, to analyze the predictor as a hash function, and to show that if I take a random seed x from the input points, the probability I would produce a predictor which is bad is less than this small number. And so basically, this is the part for which that one has to perform the probabilistic reasoning on them, and really to show why this is indeed the case. And so the lemma says that Px as an exactive hash function dispersing points somewhat randomly. And so, but what this means is that we have kind of reduced the problem to something that people in the traditional analysis of algorithm always does. So even though this is something complicated, but this is something that is within the kind of a familiar type of function that the theorists in analysis of algorithm have been doing for many years, analyzing the hash function. So I will not go into that. So that's the first step, that we are assuming all the AIs to be a single constant. And the reason that we would like to put that restriction is that when the AIs are constant, that enables us to solve the problem to use the stochastic tool to solve the problem. Because in principle, the AIs themselves depends on the sample points. So given different sample points, you will have different AIs. So that combination means that we have almost no tools to analyze the behavior of a hash function when we don't have the kind of constant linear combination as we have. And so now the reason that we can do the first step by restricting the AI to the constant is because we are saved by the learning aspect, namely that it's because we have learned the parameters in a certain way that we can carry out the first step and still would get the right conclusion. And so to remove the restriction that the AI is equal to the parity, let's consider the maximum margin condition for obtaining all the constant using optimization theory, because the criteria that we use to maximize the margin can be written, rewritten as a quadratic programming problem. And that enables us to infer that for the parameters that we have chosen, the AI can be shown to be very close to plus or minus 1, except for a term which is exponentially small in n. And this implies that our derivation in the very detailed probabilistic hashing analysis, if we examine, looking at all the steps in the derivation, when we put the AI into it, the derivation is small enough during all the derivation in the proof, and thus will not affect the conclusion that we have. And to summarize, a rigorous analysis of machine learning algorithm behavior can involve quite subtle probabilistic reasoning. Such understanding will help us build a firmer foundation for machine learning and more generally AI. And to conclude, I'm advocating that that machine learning is a rich cross-disciplinary area that can use a lot more theoretical research. Indeed, I believe that the mathematical analysis algorithm has found a great arena to play its analysis in machine learning questions, because I think that the importance of the machine learning applications means that it's very, very crucial to be able to do the analysis. And we have seen that discuss kernel method and relatedly, the deep neural networks, they are notable topics in the machine learning research, and a lot of interesting progress are being made in the theoretical aspect of these topics, and they would utilize a rich tool of techniques from optimization theory, statistical physics, information theory, etc. So it's a lot of fun. And among all the problems, I think that no area would be a great research area unless it has some notable problems that are really worth capture the imagination of people. And in this arena, there's the fundamental problem for theoretical research is why does the deep neural networks perform so well. So I think that starting with the kernel method, I think is a very good beginning. And there's no satisfactory answer in this great topic. And finally, let me just go back to the very beginning. I think that when we look at the big picture in computer science and indeed in science, and I think that the recent development of machine learning really confirms our scientists' belief all along, namely that the basic science research is very worthwhile, and conceptual breakthrough, for example, the deep learning in the 1980s, they could lead to great applications like the deep learning has yield in the AlphaZero program and the various facial recognition program that are considered a miracle today. And so the general scientific paradigm that today's theoretical explorations are laying foundation for future amazing official application. I think this is a belief that we all share. Thank you very much. So that's the end of my talk. Thank you.
Yeah, thank you so much for Professor Andy Yao's great inspiration proof and point out many interesting issues. So now let's open up for questions.
May I ask a question? Yeah.
Sure.
You can look at all these machine learning thing, okay. The data are just one type of data and with n dimensions, right? But actually in the database, you have so many different relations. They are all related. So that means that if the data come from some databases with many relations, can the system still work?
Oh, yes. I think that the I think the point is that eventually we really would like to be able to understand the machine learning algorithm to such a degree that we would have a principle for us to be able to certify whether this is a good algorithm or not. And so when we reach that point, of course, we would like to be able to handle most of the practical situation. And so I think eventually there probably will be a standard, a protocol for how to certify that a machine learning algorithm is good or not. But I think that it's a very messy problem if we want to get there, and because we have to first figure out what do we do when we are actually encountering the data which not only cannot be really described in a nice mathematical fashion, but also the data would come from different applications and also at different time they could be different. So I think that the good scientific paradigm is that we should start with simple ones, because if we can't even figure out how to certify the algorithm for mathematically well-defined subject, we will have no chance to be able to reach the final step. And so let me say that this is I think that first we start with some kind of model distributions is a good point to start. And we have experience in in computational biology, namely that many years ago, in the 1990s, when computer scientists are getting into the field of computational biology and the algorithm analysis, they would do the kind of gene analysis and the genome pattern construction algorithms. They would all assume when you do the analysis, you would all assume that the genes, the letters in a gene, they are kind of random characters from ACT. But so there's no reason why it would conform to the real distribution of real gene. But people kind of do it anyway. So to do it, to analyze things based on some unrealistic assumption. And so their experience actually is very impressive, namely that if you do it on on some mathematically well-defined case, and you analyze it, and it turns out that it correlates pretty well with the applications. So I think that the point is that the experience from science is that you do the best you can, but eventually I believe that in the case of machine learning, I believe that eventually if we can start understanding the machine learning algorithms in a very thorough manner, then we would be able to model the practical distributions in a better way. And also, I think that really there, for me, there's a very big ambitious program ahead, namely that eventually the one should want to have method of having an industry standard for certifying machine or AI algorithms in such a way that it's not totally rely on mathematical rigor, because I think we encounter problems that are very difficult to solve with 100% rigor. So eventually we have to relax the standard for mathematical analysis, and so I think that it's something that it will take a long time, and it's a very interesting direction for the theoretical research into machine learning. But I think right now, essentially people don't have a very good handle on analyzing these algorithms. And so at the risk of saying too much, so let me just say that to analyze algorithms in a analytic way is not new. I think that many years ago people started because realizing that NP complete problems, you can't have a really good algorithms in the canonical sense. So people are starting to analyze heuristic algorithms. But the difference with today is that in the old days, when you design a heuristic algorithm, say for finding a maximum click, what you do is that you have studied the problem intensively, and you put up a algorithm that have some reason that you believe that it will work. But in the machine learning case, basically all these algorithms are off the shelf. The kernel type of algorithms or the deep networks, they are general purpose problem solving machines. And there's no reason why they should work for any specific problem. And so therefore, that's also part of the reason why it is difficult. And so what this really means is that for the algorithm analysis in the past, it's very easy to decertify an algorithm. I mean, if you come up with a heuristic algorithm which only works if your intuition is right, then if it's not according to intuition, then usually it's very easy to show that kind of analytically that it doesn't work well. However, for today's this general purpose, very powerful algorithms, machine learning, they seem to have a good reason for working in all these circumstances. And so that means that actually to show something that is totally unreasonable to work, to prove that its performance is really bad. For example, in the parity case, it's not easy. And so that's a long explanation. And in summary, what I'm saying is that I think we are just at the beginning of trying to understand a mathematical foundation of machine learning, but there's a long way to go. And I have no idea what it will lead to in 10 years.
So I have another question related to your talk, okay. Just want to talk about the house price, okay, selling price, estimate.
Yes.
Because a house selling price, in fact, your input will be some sort of n-dimension relation, okay.
Yes.
I mean, looks like something like land area, building area, what type of house, etc. The location, okay. Yeah. So all these sort of thing, okay. In fact, different feature had different importance to the price. Land area, maybe the building, that one may not be so important.
Yeah.
Because people may demolish the house and then build a new one. But the
Yeah.
land area, location, etc. Okay, those are important.
Yeah.
That means the importance of each of the dimensions, each of the features are different. Usually, I mean, like in Singapore, they have something like, okay, in this area, your land area is how many $1,000 per square foot, something like that. Then you build how much, etc. And then location also.
Yeah.
So that's one thing. That means whether the AI need to know the importance of each of the dimension or not. Do you need to assign a weight, or they can just learn from the data? Because for me, they cannot learn from the data, at least for this particular application, because the housing price keep changing.
Well,
Changing within how many years? 5 years, they increase by one time also, or double the price. So that means you cannot use the old data to estimate the price. But usually, like those housing agent, they will send you some sort of information about the houses, transaction, neighbor area, what are the prices, the land area, etc. That means dimension, time dimension is a very important. I look at some of the deep learning things. Okay? Almost none of them talk about the time dimension. It's very important for certain application, many applications.
Okay, so let me answer this question. Well, firstly, that if you're talking about you want to write a program that would extrapolate and make predictions, it certainly is best to use current information. Let's say that all the houses sold last year, and that will give you, that will solve the objection that they are old data, and the second thing is that basically, I think it's certainly that the charm of the machine learning algorithms is that the dominant philosophy is saying that we don't need to know whether the land area is more important or the supposedly if you have enough data, you will be able to take everything into account, probably better than you intuitively can. But it doesn't mean that when you write a program and you shouldn't check it and to see that whether it conforms to the intuition one have, right? So, I mean, it could be that machine learning algorithms, they don't work, at least some particular type wouldn't work. So I think that it certainly has to be used with caution. And now let me mention that how to deal with the time effect. In principle, the machine learning algorithm can also deal with the time effect. Namely that if I put all the data for the last 20 years, and I can perform an analysis so that it would be, it will look at it and the time value of the shift. For example, the machine learning algorithm should be able, in principle, they should be able to recognize things like the housing market is good, the price double every 3 years, and they would take into account. So if you have, I think the belief right now is that if you look at take a very deep neural network, and you put the housing information and the time thing into it, and you want it to predict the house price in 3 years from now, it should give you a reasonable extrapolation. And of course, I'm not sure anyone has done the experiment or not. And I would love to see whether the machine learning algorithm could do it. But of course, there are always things unpredictable. For example, if there is a big forest fire, in the kind of neighboring Singapore, and suddenly this year the housing market just dropped to zero. I think so I think barring the kind of unforeseen circumstances, the claim of the machine learning enthusiasts is that it's conceivable that machine learning can read through the data and put everything kind of into a black box. So I think it's probably, it certainly should not be true when you get into things like how the human brain come up with creativity ideas. But I think that they do have a point in their philosophy. I think up to a point. I think that it's very exciting that somehow the machine will be able to take everything into account.
Yeah,
just want to add that their recent work on transformation from neural network models into probabilistic automata or probabilistic decision trees, so that they can explaining certain features. Why 80% dominate the decision, the location dominate 80% for the housing price. So that kind of analysis. So there are some recent papers on explainable AI by transformation from deep neural network into probabilistic or Markov model, or probabilistic automata or decision trees. It was some interesting work. Yeah, just try to add on to that practical side.
Yeah, I agree. I think that there's a lot of new directions that one can interact with the machine learning arena.
So the housing price also has some external factor. Just how you mentioned about like forest, but the thing like those economic crisis. Okay, yes. At one time the price dropped drastically. You cannot just use the data to figure out how come the price dropped drastically. Basically, because there's some external event occur. That external event is out of the data. It's not included in the machine language data.
Yeah, I think you're right. But yeah, I think it is a, it's a subject. I think it's a great subject to explore. That how do you take the external factors into account?
Yeah, thanks a lot.
Yeah, thank you very much.
Thank you. Any further question before we let Andy to go?
Hi, Prof. Can I ask a question?
Sure, Rofan. Yeah, go ahead.
So in this talk, thanks for your great talk. I think I have learned a lot from it. So in this talk, you give an example on estimating the parity function. So because the parity function, they take only binary inputs or high-dimensional binary inputs, and we prove that the kernel method does not work in this case, then do you think that the kernel method works better in continuous data and also in a dense data case?
I think that it's a mystery why the machine learning algorithms work in some cases and not in some other cases. I think this is sort of, in some way, it has to do with whether a problem is continuous, because I think that when you deal with continuous problems, it's in some sense a little bit easier, because in principle, the machine learning algorithms is a heuristic type of optimization algorithm. So therefore, it should work for continuous problems better. And for the Boolean case, because in Boolean functions, you could have a lot of discontinuities. So I think that in principle, there's more chance for the heuristic type of algorithms fail. But exactly, I mean, certainly for continuous problems, the kernel method also work in some cases better than in others. And I think that in answering your question is that I think it's basically unknown in the theoretical sense, that we don't have any kind of characterization of when the Gaussian kernel would work well, because in some way it's a very tough question, because the transcendental, we know the polynomials better than transcendental functions. I mean, there are a lot of study about the polynomial type of functions, and so we have more tools. But for the so I think that I think a good way to start with is with polynomial kernels. You know that because the polynomial kernels are easier to handle mathematically. So if you are interested in kind of understanding the limitation and the power of kernel functions, maybe you should start with, let's say, quadratic or cubic. I think usually people think cubic or the seventh power polynomials are better, for example, than quadratic. So I think I think even that is pretty hard, because the when you look at the experts literature on polynomials, you will find out that aside from linear case, I think all the other case, the quadratic, the cubic, already people have difficulty in understanding how they can approximate other functions. And so I think it depends. I think it's a difficult, but it's a very exciting areas to work in.
Okay, thank you, Prof.
Hi, Prof. I have another question. Yeah. Hello. Hi, Prof. May I know if you have any suggestions on how can we ensure the fairness or security of the machine learning system?
I think it's a big and exciting areas in recent years, but I'm not an expert on it. I think that well, there's I think basically the question is that certainly you can test it, right? I think that the universal methodology is that you can design certain test case of fairness and see how the machine, how the algorithm handles it. I think that's the one way of doing it. I think that's actually the easiest way to handle, because basically one can have the we can make laws saying that you have to conform to the anti-discriminatory or certain act, and you can so basically you have to have the professional the lawyer and the designer and so on getting together to design how to design a test of this kind. So that's the pragmatic operational way to solve the problem, and probably that would be the way to go, because when you look at the automatic driving, I mean, I think that's the way people will have to go in order to be able to bring the area into practice, right? I mean, but from a scientific view, it's more nuanced, and basically, suppose I think that basically, when we say that the machine learning algorithms is a black box, we don't mean that it's a total mystery in the sense of what the codes are. And basically, I think that in tomorrow's world, it probably will become a pretty standard thing for software to be open source, so that you have the code available for you to, or the experts to examine. So in that case, the question is that is it possible to do something more than the pragmatic test, to do something more fundamental? So there are ways that you can do it, and one possibility is that the algorithm designer can come up with a way to explain, I mean, how is it optimized? What are the criteria for doing the optimization? And also, how does it put into some clauses so that it will avoid a certain discriminatory action? And actually, that when you combine it with the encryption technology, I think there are even more possibilities, namely that the algorithm designer, it is possible for the algorithm designer to reveal some of the company's secret, namely that, I mean, the company, when they do it, there are certain secrets that they don't want to share. But however, using today's privacy preserving technology, it is possible. I think that certainly theoretically, it is possible to check the whether the algorithm designer actually put in the safeguard that they say that they have put in without revealing the company's secret. So I think that if you go beyond the political solution, the pragmatic and administrative solution, when you go to the scientific solution, I think that that it has to be solved scientifically, but I don't see how we can solve the security problem right now.
Yes, as for the fairness, some researchers like Xiaohui Bei have done extensive research topics between the computer science and economics, especially on the fairness in resource allocation. I think maybe those research can be combined with our machine learning research to ensure the fairness of now the neural networks or the deep learning systems or those recommendation systems fairness. Is that possible, or is that?
Yes, I think it's not only possible, but it has to happen, because because I think that the machine learning, I think it's just inevitable that the economics incentive will force everything to employ machine learning to some extent, and so when we're facing codes which are not designed with a clear motive, it's a very interesting and exciting area, as you say, how to combine all this together and design a system that are publicly trustworthy. But on the other hand, they will still maintain their efficiency.
Okay, thank you, bro. Thank you very much.
Yeah, thank you, Dr. Zhang.
Great.
So
Thank
say
you
hello
so
to
much.
say hello to Xiaohui.
Thank you.
Yeah, thank you so much. I think it's a wonderful talk, wonderful advice, follow up, answer the questions. And so let's put our hands together to thank Professor Yang.
Okay. Okay, thank you very much. And thank you, Jean. And hope to meet you one day.
Yeah, we haven't met a couple times, but I think it's much bigger conference
Okay.
context. Yeah, so let's close today's session. Just reminder, tomorrow we have a morning keynote by Professor Mushirati. I think around 9 o'clock, rather early. So again, the same link. Anyone welcome to join in. Okay.
Okay. So